Hello everyone. Today we'll study the probability of a union of events. Let me show you an example first. How do we find probability of A union B? That's a union of two events. How do we find probability of A union B? We know that there's a formula says probability of A plus probability of B minus probability of A intersection B. For probability of A union B, assume that's set A, that's set B. I first of all add probability of A and probability of B together, but we overcome the middle region. We count it twice. So in order to keep it in balance, I subtract the middle region. So I do probability of A plus probability of B minus probability of A intersection B. That's how we get probability of A union B. Next, how about probability of A union B union C? That's the union of three sets. That's the union of three events. That's the union of three events. How to find a formula for this? We can use a Venn diagram also. Let's draw a Venn diagram first. Let's use a Venn diagram to find a formula. Assume that's event A. That's event B. That's event C. We can first of all try probability of A plus probability of B plus probability of C. If I try probability of A plus probability of B plus probability of C, I have A, B, C here. It looks like I overcome some regions. If I use probability of A plus probability of B plus probability of C, I overcome some region. I overcome this region here. I overcome this region here. And I overcome this region here. So in order to keep it in balance, I will subtract probability of A intersection B, subtract probability of A intersection B, A intersection C, and B intersection C. So I first of all add probability of A, B, C, then subtract and overcome the region. I subtract this region, and this region. Do we get an actual probability? How about the middle region here? For the middle region here, initially, when I take probability of A plus probability of B plus probability of C, I add this region 3 times. Probability of A plus probability of B plus probability of C. I add this region 3 times. But then when I subtract probability of A intersection B, A intersection C, B intersection C, I subtract the middle region 3 times. When I subtract it 3 times. But I'm supposed to count it once. In order to find probability of A union B union C, I'm supposed to count it once. Since I add it 3 times, subtract it 3 times. In order to count it once, I will add probability of A intersection B intersection C. Initially, I add it 3 times. Then I subtract 3 times. There's nothing here. In order to count this region once, I will add probability of A intersection B intersection C. So that's the formula for probability of A union B union C. Now, how about probability of A union B union C and union D? What's the probability of a union of 4 sets, of 4 events? How do we find probability of union of 4 events? We can follow the same pattern here. We can first of all do probability of A plus probability of B plus probability of C plus probability of D. Add the single sets together, then subtract the intersection. Probability of A intersection B, A intersection C, A intersection D, B intersection C, B intersection D minus C intersection D. Then it looks like we subtract too many. We need to add something back. Add probability of A intersection B intersection C. Add probability of A intersection C intersection D plus probability of A intersection B intersection D. Let me write them closer. A intersection B intersection D. Probability of A intersection C intersection D. Plus probability of B intersection C intersection D. Then it looks like we add too many. We subtract probability of A intersection B intersection C intersection D. Here, do you see the pattern here? We first of all add the probability of every single set, then subtract the probability of intersection of any two sets. A intersection B, A intersection C. Subtract probability of intersection of any two sets. Then we add the probability of intersection of all three sets, any three sets. Then add the probability of intersection of any three sets. Then subtract the probability of the intersection of four sets. Then subtract the probability of intersection of four sets. The same pattern here. We first of all add the probability of single sets, and then subtract probability of intersection of two sets. Then add the probability of intersection of three sets. So the sign alternating, plus, minus, plus, plus, minus, plus, minus, and so on. Next, how about the probability of a union of n events? Probability of a union of n events. Union I from 1 to n of AI. That's the probability of a union of n events. This can be written as probability of A1 union A2 union AN. How about the probability of a union of n events? What should we do here? So follow the same pattern. Follow the same pattern. First of all, we add the probability of every single set. I is from 1 to n. I first of all add the probability of every single set. Add the probability of every single set, like what we did here. First of all, add the probability of every single set together. Then subtract the probability of every intersection of subtract the probability of intersection of any two sets. Then subtract the probability of the intersection of any two sets. Here, I and j is from 1 to n. Here, I subtract the probability of intersection of any two sets, any two events. Subtract the probability of the intersection of any two events. That's what we did here. Subtract the probability of the intersection of any two events. Subtract the probability of the intersection of any two events. Then we add. Then we add the probability of the probability of the intersection of any three events. I, j, k is from 1 to n. Probability of AI intersection AJ intersection AK. Then add the probability of the intersection of any three events. Then keep the same process. Add the intersection of the event of any three events. Add the probability of the intersection of any three events. Then subtract the probability of the intersection of any 4 events. Then add the probability of the intersection of any 5 events, and so on. The sign keep plus, minus, plus, minus, plus, minus, and so on. This is a formula for the probability of a union of n events. That's the formula for the probability of a union of n events. This formula has a name. This formula has a name. It's called the principle, the inclusion-exclusion principle. Inclusion-exclusion principle. This formula is called an inclusion-exclusion principle. That's the probability of a union of n events. That's how we find probability of a union of n events. In general, we focus on these 3 formulas. That's the probability of a union of 2 events. That's the probability of a union of 3 events. That's the probability of a union of 4 events. So in general, we focus on these 3 formulas. If there are more events for the union, we use this formula. Add the probability of any single events together, then subtract the probability of the intersection of any 2 events, then add the probability of the intersection of any 3 events, and so on. 4 events, 5 events, 6 events, 7 events, intersection of 4 events, 5 events, 6 events, and so on. The sign is alternating, plus, minus, plus, minus, plus, minus, and so on. So keep this formula in mind. Next, let's look at an example here. Last semester, there were 60 students in a math class. 35 students passed exam 1. 40 students passed exam 2. 30 students passed exam 3. 28 students passed exam 1 and 2. 22 students passed exam 2 and 3. 20 students passed exam 1 and 3. And 15 students passed all 3 exams. A student in the class is randomly asked, Part A, what's the probability that this student passed at least one of the exams? So let's set out the problem first. Let event A represent that this student passed exam 1. Let event B represent that this student passed exam 2. Let event C represent that this student passed exam 3. Next, let's write down what's given in the problem. 35 students passed exam 1. That means probability of A. Probability that this student passed exam 1 is 35 over 60. There are totally 60 students. 35 out of 60 passed exam 1. And 40 students passed exam 2. That means probability of B. Probability that this student passed exam 2 is 40 over 60. And 30 students passed exam 3. That means probability of C is 30 over 60. 28 students passed exam 1 and 2. That means probability of A intersection B. This student passed exam 1 and 2 is 28 over 60. 22 students passed exam 2 and 3. Probability of B intersection C. This student passed exam 2 and 3 is 22 over 60. And 20 students pass exam 1 and 3. Probability of A intersection C. Probability that this student pass exam 1 and 3 is 20 over 60. And 15 students pass all 3 exams. 15 students pass all 3 exams. That means probability that this student pass exam 1, exam 2, and exam 3 is 15 over 60. That's what's given. In part A, what we are looking for is what's the probability that this student pass at least one of the exams. At least one of the exams means he either pass exam 1 or exam 2 or exam 3. That means this student either pass exam 1 or exam 2 or exam 3. Then use the formula for probability of a union of events. Use the formula. We have probability of A plus probability of B plus probability of C. Add the probability of every single set. Then subtract the probability of every union of any two sets. Minus probability of a union of any two sets. Minus probability of A intersection B. Minus probability of A intersection C. Minus probability of B intersection C. Then plus the probability of intersection of any 3 sets, which is probability of A intersection B intersection C. Then plug in the values. Probability of A is 35 over 60. Probability of B is 40 over 60. Probability of C is 30 over 60 minus probability of A intersection B is 28 over 60 minus probability of A intersection C is 20 over 60. Probability of B intersection C is 22 over 60 plus probability of A intersection B intersection C is 15 over 60. Together, we add and subtract, and then add. Use calculator, we get 50 over 60, which is 5 over 6. That's the probability that this student will pass at least one of the exams. Part B, what's the probability that this student didn't pass any of the exams? That means this student, he didn't pass exam 1, and he didn't pass exam 2. And he didn't pass exam 3. If we use De Morgan's law, that can be rewritten as probability of A union B union C complement. If we use De Morgan's law, that can be rewritten as probability of A union B union C complement. That's 1 minus probability of A union B union C. From part A, we know that probability of A union B union C is 5 over 6. That's probability of A union B union C is 5 over 6. One minus 5 over 6 is 1 over 6. So the probability that this student didn't pass any of the exams is 1 over 6. Part C. What is the probability that this student pass at least 2 of the exams? Part C. what's the probability that this student passed at least 2 of the exams? So let's draw a Venn diagram and see how it looks like. What's the probability that this student passed at least 2 of the exams? Let's draw a Venn diagram. Assume that's event A, that's event B, that's event C. What's the probability that this student pass at least 2 of the exams? That means he must pass at least 2 of the exams, either exam 1 and 2, exam 1 and 3, or exam 2 and 3. He has to pass at least 2 of the exams, either exam 1 and 2, exam 1 and 3, or exam 2 and 3, or all 3 exams. So for the shaded region here, all we can do is we can try probability of A intersection B plus probability of A intersection C plus probability of B intersection C. Take probability of A intersection B plus probability of A intersection C plus probability of B intersection C. But here, if we add it this way, we overcome the middle region. We're supposed to count every region exactly once. But here, when I take probability of A intersection B plus probability of B intersection C, A intersection C plus probability of B intersection C, I add the middle region 3 times. I'm supposed to add it only once, but here I add it 3 times. I add the middle region 3 times. In order to keep it in balance, I need to subtract the middle region twice. Here, since I add the middle region 3 times, I'm supposed to add it only once, but since I add it 3 times, in order to keep it in balance, I subtract the middle region twice. I subtract twice probability of A intersection B intersection C. Since I overcome the middle region 3 times, I'm supposed to count it only once. I overcome it twice, so take away 2 of them. Then from part A, we know that probability of A intersection B, probability of A intersection B is 28 over 60. Probability of A intersection C is 20 over 60. Probability of B intersection C is 22 over 60. Minus twice probability of A intersection B intersection C. A intersection B intersection C is 15 over 60. So probability of A intersection B intersection C is 15 over 60. Then adding up and subtract, we have 70 over 60 minus 30 over 60, which is 40 over 60. That's 2/3. So the chance that this student will pass at least 2 of the exams is 2/3. Next example, a hand of 5 cards is dealt to each of the 3 players, player 1, player 2, and player 3, from a standard deck of 52 cards. Part A, what's the probability that player 1 receives exactly 1 ace? Part B, what's the probability that either player 1 or player 2 receive exactly 1 ace? Part C, what's the probability that at least one of the players receive exactly 1 ace? So let's set out the problem first. Let event A represent that player 1 receive exactly 1 ace. Let event B represent player 2 receive exactly 1 ace. The event C represents player 3 receive exactly 1 ace. The event C represents player 3 receive exactly 1 ace. In part A, what we are looking for is what's the probability that player 1 receive exactly 1 ace. So in part A, what we are looking for is probability of A. What's the probability that player 1 receive exactly 1 ace? So keep in mind that probability is always number of available outcome divided by the number of all possible outcome. We can find the number of all possible outcome first. There are totally 52 cards. 3 players. Each player deal 5 cards. Each player deal 5 cards. So when we draw cards, the order of getting cards doesn't matter. What we care is what card we get. We don't care which card we get first. So when we draw cards, order doesn't matter. We use combination. Now, first player will draw 5 cards out of 52. So first player can draw 5 cards out of 52 in these many ways. First player can draw 5 cards out of 52 in these many ways. Now for the second player, since first player draw 5 cards already, there are 47 cards left for the second player. Since first player draw 5 cards already, there are 47 cards left for the second player. Second player also draw 5 cards, but the second player draw 5 cards out of 47. So the second player can draw 5 cards out of 47 in these many ways. Then for the third player, there are 42 cards left. There are totally 52 cards. Each player draw 5 cards. There are 42 cards left for the third player. Third player also draw 5 cards, but he draw 5 cards out of 42. So the third player can draw 5 cards in these many ways. Since first player can draw 5 cards in this many ways, second player can draw 5 cards in this many ways, and the third player can draw 5 cards in this many ways. By counting principle, we have this many ways. We multiply this together. These 3 players have this many ways to draw 5 cards. By counting principle, we multiply this together. Now that's the denominator. Numerator, number of favorable outcome. Number of favorable outcome. What we want is first player 1 receive exactly 1 aces. Player 1 receive exactly 1 aces. Player 1 draw 5 cards. 1, 2, 3, 4, 5. One of the cards must be aces. And we know that there are totally, in the standard deck, there are totally 4 aces. Other than 4 aces, there are 48 other cards. In the standard deck, there are 4 aces. Other than aces, we have 48 other cards. Now, first player, he draw 1 aces out of 4. First of all, he draw 1 aces out of 4. So he has this many ways. He has this many ways to draw 1 aces out of 4. Next, he will draw 4 other cards. Since he received exactly 1 aces, the other 4 cards cannot be aces. The other cards cannot be aces. So those are non-aces cards. The other 4 cards cannot be aces. He must draw 4 non-aces cards. So he draw 4 cards from here, from other cards. He draw 4 cards from the other cards. The number of ways of drawing 4 cards out of 48 is 48 choose 4. That's the number of ways he draw 4 cards out of 48. Then that's player 1. We only care about player 1. We don't care about player 2 and 3. Then for the rest, for player 2 and 3, we mix the rest of the cards together. There are totally 52 cards. Player 1 draw 5 cards. There are 47 cards left. Player 2 draw 5 cards out of 47. Then there are 42 cards left. Player 3 draw 5 cards out of 42. That's the numerator, number of favorable outcome. That's the number of ways that the first player receive exactly 1 aces. Then simplify. I can cancel 47 choose 7, 42 choose 5. What's left is 4 choose 1 times 48 choose 4. Over 52 choose 5. Then use calculator, we can get the answer using calculator. Part B. What's the probability that either player 1 or player 2 receive exactly 1 aces? So we're looking for probability of A union B. What's the probability that either player 1 or player 2 receive exactly 1 aces? Then use the formula. That's probability of A plus probability of B minus probability of A intersection B. Probability of A represents that the first player receive exactly 1 aces. Probability of B represents the second player receive exactly 1 aces, which is the same. There's no difference between the first player and second player. Probability of A is the same as probability of B. And from part A, we found probability of A. From part A, we found probability of A is 4 choose 1 times 48 choose 4 over 52 choose 5. That's probability of A and probability of B. Next, let's find probability of A intersection B. Probability of A intersection B represents the probability that the first player receives exactly 1 aces and the second player receives exactly 1 aces. So let me show you the picture here. In a standard deck, there are 4 aces. And other than aces, there are 48 other cards. Other than aces, there are 48 other cards. Probability of A intersection B represents that the first player receives exactly 1 aces and the second player receives exactly 1 aces. So first player receives exactly 1 aces. Second player receives exactly 1 aces. The rest of the cards cannot be aces. Since they receive exactly 1 aces, the rest of the cards cannot be aces. The rest of the cards cannot be aces. Now, probability is always the number of favorable outcome divided by the number of all possible outcome. Probability is always number of favorable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. There are totally 52 cards. We have 3 players. Each player draws 5 cards. So for the first player, he draws 5 cards out of 52. Then there are 47 cards left. Second player draws 5 cards out of 47. For the third player, there are 42 cards left. The third player draws 5 cards out of 42. That's the denominator, the number of all possible outcomes. That's the total number of ways that each player draws 5 cards out of 52. Now the numerator, number of favorable outcome. A intersection B represents that the first player receives exactly 1 aces and the second player receives exactly 1 aces. For the first player, he draws 1 aces out of 4. That's 4 choose 1. Then he needs to draw 4 other cards out of 48. That's 48 choose 4. Second player, he needs to draw another aces. But since first player picked 1 aces already, there are 3 aces left. Second player can choose 1 aces out of 3 in this many ways. So he can choose 1 aces out of 3 in this many ways. That's combination 3 choose 1. Then he needs to choose 4 other cards. Out of 48 cards here, first player already picked 4 cards. So there are 44 cards left. Second player also needs 4 cards from here. So from these 44 cards, he draws 4 cards. Now for the third player, we don't care. We don't care what he gets. Then we mix the rest of the cards together. There are totally 52 cards. First player picked 5 cards. Second player picked 5 cards. So there are 42 cards left. we mix the rest of the card together. The third player, we don't care what he get. He chose 5 cards out of 42. That's the probability of A intersection B. Then for probability of A union B, we use probability of A plus probability of B minus probability of A intersection B. Here I can cancel 42 choose 5, make it a little easier. It's 4 choose 1, 48 choose 4 times 44 choose 4 times 3 choose 1 times 44 choose 4. The denominator is 52 choose 5 times 47 choose 5. Then plug into the formula. Probability of A plus probability of B, since they are the same, we can write twice 4 choose 1 times 48 choose 4 over 52 choose 5 minus probability of A intersection B, which is this, minus 4 choose 1 times 48 choose 4 times 3 choose 1 times 44 choose 4 over 42 choose 5, 47 choose 5. Then use calculator for the answer. Use calculator for the answer. Part C. What's the probability that at least one of the players receive exactly 1 aces? So for part C, we're looking for a probability that either first player receive 1 aces, or the second player receive exactly 1 aces, or the third player receive exactly 1 aces. Use the formula. We first of all add the probability of every single sets, every single events. Subtract the probability of the intersection of any 2 events. Subtract the probability of the intersection of any 2 events. We have A intersection B, A intersection C, minus B intersection C. Then add the probability of the intersection of any 3 events. And the probability of the intersection of any 3 events. We have probability of A intersection B intersection C. We know that from part A, we know probability of A. From part A, we know probability of A is 4 choose 1 times 48 choose 4 over 52 choose 5. And we know that probability of A, probability of B, probability of C, they're all the same. From part B, we know that probability of A intersection B is this. From part B, we know this is probability of A intersection B. This is probability of A intersection B. So probability of A intersection B is 4 choose 1, 48 choose 4, times 3 choose 1, 44 choose 4, over 52 choose 5, times 47 choose 5. And similarly, we know that probability of A intersection C, B intersection C is the same as probability of A intersection B. A intersection B, A intersection C, and B intersection C, they are exactly the same. Then next we need to compute probability of A intersection B, intersection C. Next, we try to compute the probability of A intersection B, intersection C. So same thing, let me draw a picture. in a standard deck, there are 4 aces. Other than aces, there are 48 other cards. There are 3 players. Each player receives exactly 1 aces. So the first player receives exactly 1 aces. The other 4 cards are non-aces. Second player receives exactly 1 aces. The other 4 cards are non-aces. Third player receives exactly 1 aces. The other 4 cards are non-aces. Now, probability is always number of viewable outcome divided by the number of all possible outcome. In how many ways can 3 players draw 5 cards? Can each of the 3 players draw 5 cards from a standard deck of 52 cards? First player draw 5 cards out of 52. Then there are 47 left for the second player. Second player draw 5 cards out of 47. Then there are 42 cards left. The third player draw 5 cards out of 42. That's the number of ways that each of the 3 players draw 5 cards out of 52 cards. That's the denominator, the number of all possible outcome. For the numerator, the number of favorable outcome will be 1. First player draw 1 aces out of 4. So he has this many ways to draw 1 aces out of 4 aces. The number of ways to draw 1 aces out of 4 is combination 4 choose 1. Then he should draw 4 cards other than aces. He draw 4 cards from 47. From 48. The number of ways of draw 4 cards out of 48. That's 48 choose 4. Then for the second player also need to draw exactly 1 aces. Since first player picked 1 aces already, there are 3 aces left. So second player draw 1 aces out of 3. He has this many ways to draw 1 aces out of 3. Then he have 4 cards other than aces. From these other cards, first player picked 4 cards already, so there are 44 cards left. Second player will draw 4 cards out of 42. That's the number of ways he draw 4 cards out of 44. Next, for the third player, since there are 4 aces, the first 2 players, each player already picked 1 aces. Then there are 2 aces left. Since there are 4 aces, first player and the second player, each player get 1 aces already. So there are 2 aces left here. For the third player, he chose 1 aces out of the 2 remaining aces. Now, the third player also needs 4 other cards. There are totally 48 other cards. First player draw 4 cards from here. Second player draw 4 cards from here. So there are 40 cards left for the third player. Third player draw 4 other cards. Draw 4 cards other than aces from here. It's 40 choose 4. So that's the number of ways each player draws 1 aces. That's the number of ways that each player draws 1 aces. That's probability of A intersection B intersection C. Then plug in for probability of A union B union C. We have probability of A plus probability of B plus probability of C. Since they are all the same, we can take 3 times this number. 3 times 3 times 4 choose 1 times 48 choose 4 over 52 choose 5 minus A intersection B minus A intersection C minus B intersection C. But since probability of A intersection B, A intersection C, B intersection C, they're all the same and they all equal to this, I can take 3 times this number. So minus 3 times this number, that's 4 choose 1 times 48 choose 4 times 3 choose 1 times 44 choose 4. over 52 choose 5. 47 choose 5. Then plus probability of A intersection B intersection C plus this number. We have 4 choose 1. 48 choose 4. 3 choose 1. Let me put it here. 4 choose 1. 48 choose 4 times 3 choose 1. 44 choose 4 times 2 choose 1. 40 choose 4. Then the denominator is 52 choose 5. 47 choose 5. Times 42 choose 5. Then use calculator for the answer. Type everything to the calculator. Use calculator, get the answer. Next, we will study conditional probability. Before I introduce what it is, let's look at a simple example first. When 3 coins are tossed, if it's known that there are more heads than tails, what's the probability that all 3 coins come up heads? When 3 coins are tossed, if it's known that there are more heads than tails, what's the probability that all 3 coins come up heads? Let's try to draw the sample space first. When we toss 3 coins, how many possible outcomes do we have? Let's try to draw the sample space first. Let's try to write down all possible outcomes when we toss 3 coins. We may have head, 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 tail, head, tail, head, or head, tail, tail, or tail, head, head, tail, head, tail, 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 head, or tail, tail, tail. When we toss 3 coins, there are 8 possible outcomes. If it's known that there are more heads than tails, if it's known that there are more heads than tails, means it's possible we have all 3 heads, 2 heads, 1 tail, 2 heads, 1 tail, 2 heads, 1 tail. If it's known that there are more heads than tails, that means we only consider this part now. If it's known that there are more heads than tails, if we know it's one of these 4 outcomes, if it's known that there are more heads than tails, that means if we know the outcome is one of these 4 outcomes, what's the probability that all 3 coins come up heads? What's the probability that all 3 coins come up heads? We know that probability is always the number of favorable outcomes divided by the number of all possible outcomes. Here, the number of favorable outcomes is head, head, head. That's the only one. Only this one is what we want. All 3 coins come up heads. That's the only one we want. So that's 1. Number of favorable outcomes is 1. That's only one outcome. Is our favorable outcome. Now, number of all possible outcomes. If it's known that there are more heads than tails, those are all possible outcomes. The rest are impossible. If it's known that there are more heads than tails, those are numbers of all possible outcomes. That's 4. So probability equals to number of favorable outcomes divided by number of all possible outcomes, which is 1/4. So if it's known that there are more heads than tails, the probability that all 3 coins come up heads is 1/4. Next example, when 2 dice are rolled, if it's known that none of the dice come up with a 2, what's the probability that the sum of the dice is 7? When 2 dice are rolled, if it's known that none of the dice come up with a 2, what's the probability that the sum of the dice is 7? So let's try to draw the sample space first. When 2 dice are rolled, how does the sample space looks like? When 2 dice are rolled, how does the sample space looks like? Simple space is the set of all possible outcomes. Two dice making up 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. That's a simple space, the set of all possible outcomes. If it's known that none of the dice can up 2, what's the probability that the sum of the dice is 7? If it's known that none of the dice can up 2, so none of the dice can be 2. This row is impossible. This row is impossible. This column is impossible. None of the dice can up 2. So this row is impossible. This column is impossible. Now what's the simple space now? Probability is always number of favorable outcome divided by the number of all possible outcome. How many favorable outcomes do we have? The sum of the dice is 7. We know that 1 plus 6 is 7. 3 plus 4 is 7. 4 plus 3 is 7. And 6 plus 1 is 7. So we have 4 favorable outcomes. We have 4 favorable outcomes. The sum of the dice is 7. 1, 6, 3, 4, 4, 3, 6, 1. We have 4 favorable outcomes. How many possible outcomes do we have? Since we know that none of the dice is 2, the number of possible outcomes is 1, 2, 3, 4, 5. Each row has 5 outcomes. And there are 5 rows. Since I crossed on this row, there are 5 rows here. Each row has 5 outcomes, and there are 5 rows. There are 25 possible outcomes. The number of possible outcomes is 25. If none of the dice can up 2, there are 25 possible outcomes. So the probability, if it's known that none of the dice can up 2, the probability that the sum of the dice is 7 is 4 over 25. So that's how we find probabilities. Now we can see that here in both problem 1, problem 2, there's a condition here. Something is known. In both these examples, 1 and 2, there's a condition. Something is known. If there's a condition in a problem, this probability is called conditional probability. If this probability is based on some condition, this is called conditional probability. If a probability is based on some condition, this is called conditional probability. But the thing is, we are not able to draw sample space in general. If we can draw sample space, of course, that's easy. If we can draw sample space, of course, that's easy. But in general, we are not able to draw sample space. In general, sample space are huge. We are not able to draw sample space. So we can solve it this way. I'll show you a new way to solve conditional probability. Next, I'll show you a new way to solve conditional probability. Let me first of all give you the definition for conditional probability. Let A and B be 2 events. Let A and B be 2 events with probability of B not equal to 0. let A and B be two events with probability of B not equal to 0. The conditional probability of A given the occurrence of B is defined as probability of A given B equal to probability of A intersection B over probability of B. This is read probability of A given B. This is read probability of A given B. Probability of A given B is probability of A intersection B over probability of B, where B is the condition. That's the probability we are looking for. We're looking for probability of A under condition B. B is a condition. We're looking for probability of A under condition B. And B is always the denominator. Probability of B. This B always go to denominator. For the numerator, take the intersection of A and B. And this B always go to denominator. So that's the formula. Probability of A given B is always probability of A intersection B over probability of B. Next, let's redo the previous problem using the definition of conditional probability. So in the first problem, let's translate first. When 3 coins are tossed, if it's known that there are more heads than tails, so let event A represent that there are more heads than tails. What's the probability that all 3 coins come up heads? Let B be the event that all 3 coins come up heads. What we are looking for is a conditional probability. If it's known that there are more heads than tails, something is known, something is given, it's called a condition. Something is known or given is called a condition. So here the condition is A. If it's known that there are more heads than tails, what's known or given is called condition. So here event A is a condition. What we are looking for is what's the probability that there are more coins? What's the probability that all 3 coins come up heads? What we are looking for, go to the front. What's known or given is the condition, go to the back. And what we are looking for, go to the front. We are looking for the probability that all 3 coins come up heads. So what we are looking for, go to the front. What's given as a condition, go to the back. Then use the formula. Use the formula, we first of all take intersection. Probability of A intersection B. Using the formula, we first of all take intersection, then divide by the probability of the condition. Here the condition is probability of A. The condition is probability of A. Then we can find each probability individually, get an answer, then divide. Then we can find each probability individually, get an answer, and then divide. What's probability of A? Remember, for probability is always number of feasible outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. When we flip a coin, there are 2 outcomes. When we flip 2 coins, 2 times 2, there are 4 outcomes. When we flip 3 coins, 2 times 2 times 2. Since each coin has 2 outcomes. Together, 2 times 2 times 2, there are 8 outcomes. That's the denominator. Number of all possible outcomes. A coin can come up in 2 ways. 3 coins can 2 coins can come up in 2 times 2 ways. 3 coins can come up in 2 times 2 times 2 ways, which is 2 to the power 3. That's the denominator, number of all possible outcomes. Now numerator, number of favorable outcomes. For event A, we want more heads than tails. If there are more heads than tails, that means either they come up all 3 heads, 2 head, 1 tail. There are 4 possible outcomes. There are 4 favorable outcomes, more heads than tails. Either they are all 3 heads, 2 heads, 1 tail. So there are 4 favorable outcomes. Simplify, we get 4 over A, which is half. That's probability of A. Next, find probability of A intersection B. Next, find probability of A intersection B. Probability is always number of favorable outcome divided by the number of all possible outcome. Number of all possible outcome. When we flip 3 coins, each coin can come up in 2 different ways. So 3 coins can come up in 2 to the power 3, 8 different ways. That's the number of all possible outcome. How about number of favorable outcome? There are more heads than tails, and all 3 coins come up heads. If all 3 coins come up heads, it guarantees there are more heads than tails. If all 3 coins come up heads, it guarantees more heads than tails. So probability of intersection B is the same as probability of B. All 3 coins come up heads. All 3 coins come up heads. There's only one outcome here. Head, head, head. Which is 1 over 8. Then use the formula. Probability of B given A is probability of A intersection B over probability of A, which is 1 over A. Probability of A intersection B is 1 over A, over probability of A, which is 1 over 2. Simplify, we get 1 over 4, which is the same as what we have here. In general, using the formula for conditional probability can make the problem easier. In general, when a problem is very complicated, using this formula, it can make the problem much, much simpler. Now, example 2. Let's use the new definition for conditional probability to solve this problem. Let's translate the problem first. When 2 dice are rolled, if it's known that none of the dice come up 2, let event A represent that none of the dice come up 2. Let event A represent none of the dice come up 2. What's the probability that the sum of the dice is 7? Let B be the event that the sum of the dice is even, is 7. The sum of the dice is 7. The sum of the dice is 7. We know that probability of, now what are we looking for here? It's known that none of the dice come up 2. What's given as a condition, go to the back. What's given as a condition, go to the back. What's given is that none of the dice come up 2. What's given as a condition, go to the back. What's given is that none of the dice come up 2. That's what's given. That's a condition, go to the back. What we are looking for is, what's the probability that the sum of the dice is 7? The sum of the dice is 7. That's what we are looking for. So go to the front. The sum of the dice is 7. That's what we are looking for. Go to the front. Please go to the front. Then if we use the formula, that's probability of A intersection B. So the numerator is the intersection of these 2 sets. The numerator is the intersection of these 2 sets. The denominator is a condition. This is a condition. The denominator is always a condition. That's probability of A. That's the denominator. Denominator is always a condition. Then we find probability of A intersection B and probability of A individually. Find each probability individually. Then plug in here. Then we find each probability individually, then plug in here. Let's find denominator first. Let's find the condition first. Let's find probability of A first. What's probability of A? Remember, probability is always number of favorable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. When two dice are rolled, each die can come up in 6 different ways. A die has 6 faces. Each die can come up in 6 different ways. So 2 dice can come up in 36 ways. That's the denominator, all possible outcome. The numerator is the number of favorable outcome. What we want is none of the dice come up 2. If a die doesn't come up 2, it may come up 1, 3, 4, 5, 6. So it can come up in 5 different ways. If a die doesn't come up with a 2, it can come up in 5 different ways. So each die can come up in 5 different ways. One die can come up in 5 ways. 2 die can come up in 5 times 5 ways. Since one die can come up in 5 ways, and 2 dice can come up in 5 times 5 different ways. Multiply together, that's 25 over 36. That's probability of A. How about probability of A intersection B? Probability of A intersection B do the same thing. Probability is always number of favorable outcome divided by the number of all possible outcome. Probability of A intersection B, any probability is always number of favorable outcome divided by the number of all possible outcome. For the number of all possible outcome, when we roll 2 dice, we know each die can come up in 6 different ways. And we are rolling 2 dice. 2 dice can come up in 6 times 6 different ways. That's the denominator, the number of all possible outcome. For the numerator, number of favorable outcome. Number of favorable outcome. We must consider both A intersection B. We must consider both A and B. None of the dice come up 2. The sum of the dice is 7. If the sum of the dice is 7, it could be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. That's the case that the sum of the dice is 7. But none of the dice come up 2. So 2, 5 is impossible. 5, 2 is impossible. So there are 4 possible outcomes. There are 4 favorable outcomes. Simplify, we get 4 over 36. Then we take the numerator, divide by the denominator. Probability of A intersection B is the numerator. Probability of A is the denominator. Then when we divide, flip the button over, we get 4 over 25. Cancel 36, we get 4 over 25. That's the same as what we have here. In general, using conditional probability, using this formula, using this formula can make the problem easier. In general, if we use this formula, in general, it can make the problem easier. In general, for conditional probability, there are some keywords. Such as if, no one, or given. When we see these keywords, we can usually think of conditional probability. When we see these keywords here, if, no one, or given, when we see these keywords, we can think of probabilities, conditional probabilities. Next, let's look at another example. A bag contains 2 blue marbles, 3 green marbles, and 5 red marbles. So a bag contains 2 blue marbles, 3 green marbles, 5 red marbles. There are totally 10 marbles. 4 marbles are randomly selected from the bag. Part A. If it's known that both blue marbles are selected, what's the probability that the other 2 marbles are red? So this problem looks like conditional probability. Something is known as a condition. It looks like conditional probability. So let's set down the problem first. Let's translate first and set it up. Let A be the event that both blue marbles are selected, which means two of the marbles are blue. Two of the selected marbles are blue. That's given as a condition. Also, the probability that the other two marbles are red. Let B represent the event that the other two marbles are red. That means two of the selected marbles are red. Two of the selected marbles are red. What we are looking for is probability given A as a condition, given that both blue marbles are selected. What's the probability that the other two marbles are red? So given A as a condition, what we are looking for is probability of B. Two of the selected marbles are red. So what's given is that both blue marbles are selected. So A is given as a condition. What we are looking for is the other probability that the other two marbles are red, which is B. So what we are looking for is go to the front. What's given as a condition, go to the back. What we are looking for, go to the front. What's given as a condition, go to the back. Then use the formula. That's probability of A intersection B over the probability of the condition. What's on the back is a condition. Then we find each probability individually and then put it back. We find each probability individually, then put the answer back. Let's find probability of A first. Probability is always number of favorable outcome divided by the number of all possible outcome. Number of favorable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. There are 10 marbles. 4 marbles are randomly selected. In how many ways can we choose 4 marbles? First of all, let's decide. Do we use combination or permutation? Does an order matter? Here we only care what marble we get. We don't care which marble we get first. In this problem, we only care what marble we get. We don't care which marble we get first. So the order doesn't matter. In this problem, order doesn't matter. If order doesn't matter, we use combination. So there are totally 10 marbles. We are choosing 4. In 10 choose 4 ways, in this many ways, we can choose 4 marbles out of 10. The number of ways of choosing 4 marbles out of 10 is 10 choose 4. That's the number of ways of choosing 4 marbles out of 10. Next, the numerator is the number of favorable outcome. Numerator is the number of favorable outcome. 2 of the selected marbles are blue. So the blue marble must be selected. 2 blue marbles must be selected. There are totally 2 blue marbles. We choose 2 blue marbles out of 2. Then, since we need a total of 10 marbles, since we need a total of 4 marbles, we get 2 marbles already. The other 2 marbles must be either green or red. The other 2 marbles could be either green or red. Green marble and red marble together, they are 8 marbles. Green marble and red marble together, they are 8 marbles. We're choosing 2 marbles out of these 8 marbles to form a 4 marble selection. That's probability of A. Next, let's find probability of A intersection B. For probability of A intersection B, that's a probability. Probability is always number of favorable outcome divided by number of all possible outcome. We can find the number of all possible outcome first. We are choosing 4 marbles out of 10, and order doesn't matter. The number of ways to choose 4 marbles out of 10 is 10 choose 4. That's the denominator, number of all possible outcomes. Now numerator, number of feasible outcomes. It must satisfy both conditions here, A intersection B. 2 of the selected marbles are blue, and 2 of the selected marbles are red. That means we get 2 blue marbles and 2 red marbles. There are 2 blue marbles, we choose 2 out of 2. And there are 5 red marbles, we choose 2 out of 5. Then put it back to the formula. A intersection B, probability of A intersection B, put it on the top. Probability of A, go to the bottom. So probability of B given A is 2 choose 2 times 5 choose 2 over 10 choose 4 over 2 choose 2 times A choose 2 over 10 choose 4. Then when we divide, we can cancel the common denominator. We have 2 choose 2 times 5 choose 2 over 2 choose 2 times A choose 2. 2 choose 2 can cancel. We have 5 choose 2 over A choose 2. Then 5 choose 2 is let me put it here. 5 choose 2 is 5 factorial over 5 minus 2 is 3 factorial times 2 factorial. A choose 2 is 8 factorial over 8 minus 2 is 6 factorial times 2 factorial. When we divide, we keep the top the same, flip the bottom over. It's 5 factorial times 3 factorial times 2 factorial times 6 factorial times 2 factorial times 8 factorial. Cancel 2 factorial from top and the bottom. 5 factorial over 3 is 5 times 4. 6 factorial over 8 factorial is 7 times 8 on the bottom. Then if I cancel, I have 5 over 14. That's the conditional probability. If it's known that both blue marbles are selected, what's the probability that the other 2 marbles are red? And that's the probability. Part B, if it's known that none of the selected marbles are red, what's the probability that all 3 green marbles are selected? So this problem, it has a keyword no one here. It looks like conditional probability. Let's set out the problem first. Let A represent the event that none of the selected marbles are red. That's given as a condition. None of the selected marbles are red. None of the selected marbles are red. Let B be the event that all 3 green marbles are selected. All 3 green marbles are selected. That means 3 of the selected marbles are green. 3 of the selected marbles are green. We're looking for probability that it's known none of the selected marbles are red. What's the probability that all 3 green marbles are selected? So here, what's given as a condition is A. None of the selected marbles are red. What's given as a condition is A, event A. None of the selected marbles are red. What we are looking for is the probability that all 3 green marbles are selected. That means 3 of the selected marbles are green. So what we are looking for is probability of B. What's given as condition is A. So event B is what we are looking for. Event A is given as a condition. Then use the formula. Use the formula. That's probability of A intersection B over probability of A. The condition is always the denominator. Then we find each probability individually and then divide. Let's find probability of A first. Usually find denominator first. Probability is always number of favorable outcome divided by the number of all possible outcome. Here, the number of all possible outcomes, there are totally, for the number of all possible outcomes, there are totally 10 marbles. We are choosing 4 marbles out of 10. There are totally 10 marbles. We are choosing 4 marbles out of 10. And in this problem, we only care about the color of the marble. We don't care which marble we get first. In this problem, we only care about the color of the marbles. We don't care which marble we get first. So that's combination. The number of ways of choosing 4 marbles out of 10 is 10 choose 4. That's the number of ways of choosing 4 marbles out of 10. That's the denominator. For the numerator, number of favorable outcome, none of the selected marbles are red. If we don't get red marble, means we get either blue or green marbles. If we don't get red marble, means we get either blue or green marbles. Blue or green marble together, they are 5 marbles. Blue marble and green marble together, they are 5 marbles. We are choosing 4 marbles out of these 5 marbles. We are choosing all 4 marbles out of these 5 marbles here. That's probability of A. That's the denominator. For the numerator, probability of A intersection B. This is a probability. Keep in mind that probability is always number of favorable outcome divided by the number of all possible outcome. So let's find the denominator first. Number of all possible outcome. We are choosing 4 marbles. We are choosing 4 marbles out of total of 10. And the number of ways of choosing 4 marbles out of 10 is 10 choose 4. Since order doesn't matter, we use combination. 10 choose 4. The numerator is number of favorable outcome. We must consider both A and B. A intersection B, we must consider both event A and event B. None of the selected marbles are red, and 3 of the selected marbles are green. None of the selected marbles are red. 3 of the selected marbles are green. The only possibility is green, green, green. Since it cannot be red, it must be the other one. The last one must be blue. The only possibility is green, 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 blue. That's the only possibility. None of the marbles are red. 3 of the selected marbles are green. The only possibility is green, 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 blue. So for 3 green marbles, we choose 3 green marbles out of 3. 3 choose 3. That's the number of ways of choosing 3 green marbles out of 3. There are only 3 green marbles. We choose 3 out of 3. Now blue marble. There are totally 2 blue marbles. We choose 1 out of 2. That's combination 2 choose 1. So that's the numerator here. That's the denominator. Then put them together. For probability of B given A, we use probability of A intersection B over probability of A. Probability of A intersection B is this. Three choose 3 times 2 choose 1 over 10 choose 4. Probability of A is 5 choose 4 over 10 choose 4. Then use calculator for the rest. Use calculator, we can get an answer. Part C. If it's known that one of the selected marbles is red, what's the probability that all 4 selected marbles are red? So this problem looks like a conditional probability. Let's translate the problem first. If it's known that one of the selected marbles is red, so let A be the event that one of the selected marbles is red. Let A be the event that one of the selected marbles is red. What's the probability that all 4 selected marbles are red? Let B be the event that all 4 selected marbles are red. So here, what's given as a condition is event A. What's known is that one of the selected marbles is red. So A is known as a given as a condition. What we are looking for is what's the probability that all 4 selected marbles are red. What we are looking for is event B. So we're looking for event B given A. What's given as a condition? What's given as a condition is the second part. The first part is what we are looking for. And the second part is what's given as a condition. The first part is what we are looking for. Here, event A is given as a condition. Event B is what we are looking for. All 4 selected marbles are red. Event B is what we are looking for. Event A is given as a condition. Then use the formula. That's probability of A intersection B over probability of A. Then we find each denominator and numerator individually. Then divide the answer. Let's find probability of A first. Usually find denominator first. Probability of A says one of the selected marbles is red. If one of the selected marbles is red, we know that there are 2 blue marbles, 3 green marbles, 5 red marbles. There are totally 10 marbles. If one of the selected marbles is red, it's possible that we have 1 red marble, 2 red marble, 3 red marble, or 4 red marble. If one of the selected marbles is red, we may have 1 red marble, 2 red marble, 3 red marble, or 4 red marble. There are too many cases. Let's think of A complement first. Then use the A complement to find A. What's A complement? One of the selected marbles is red. The complement is none of the selected marbles are red. The complement is none of the selected marbles are red. So let's find the probability that none of the selected marbles are red first. Probability is always number of variable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. There are totally 10 marbles. We are choosing 4 out of 10. In this problem, we only care about the color of the marble. We don't care which marble we get first. So an order doesn't matter. If an order doesn't matter, we use combination. We are choosing 4 marbles out of 10. Order doesn't matter. Let's 10 choose 4. So we have this many ways to choose 4 marbles out of 10. That's the denominator. Numerator, A complement. None of the marbles are red. That's the favor. None of the selected marbles are red. Let's find the number of variable outcome first. None of the selected marbles are red. If we don't choose red marble, that means we must choose either blue or green marbles. Totally, there are 5 marbles together. For blue or green marble, totally there are 5 marbles together. We are choosing 4 marbles out of these 5 marbles. We are choosing 4 marbles out of these 5 marbles. If none of the selected marbles are red, that means we're choosing either blue marble or green marble. And together, 2 blue marbles, 3 green marbles together, there are 5 marbles. And all 4 marbles must be either blue or green. So that's 5 choose 4. We are choosing 4 marbles from here. Then that's probability of A complement. For probability of A, we use 1 minus its complement. For probability of A, we use 1 minus its complement. That's probability of A. Next, let's try to find probability of A intersection B. Probability is always number of variable outcome divided by number of all possible outcome. For the number of all possible outcome, we are choosing 4 marbles out of 10. Order doesn't matter, we use combination. That's the denominator, 10 choose 4. Now for numerator, number of variable outcome, we must consider both event A and B. For number of variable outcome, we must consider both event A and B. One of the selected marbles is red. All 4 selected marbles are red. event B contains A. If all four selected marbles are red, it guarantees one of the selected marbles is red. So event B contains event A. Event B guarantees event A. So this find the probability that all four selected marbles are red. Let's find the probability that all four selected marbles are red. If we only choose red marble, we can only choose from this 5 red marble here, which is probability of 5 choose 4. If all 4 selected marbles are red, we can only choose red marble from here. And we're choosing 4 marble out of 5. That's 5 choose 4. That's the numerator. So for probability of B given A, that's probability of A intersection B over probability of A. That's the numerator. 5 choose 4 over 10 choose 4. The denominator is probability of A is this. 1 minus 5 choose 4 over 10 choose 4. Then we can use calculator for the answer. Next example. 5 cards are drawn from a standard 52 card deck. Part A. If it's known that at least 3 of the drawn cards are aces, what's the probability of getting a full house? Full house looks like this, something like 2, 2, 2, 9, 9. 3 cards of a kind, 2 cards of another kind, or jack, 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 queen, queen. 3 cards of a kind, 2 cards of different kind. That's called full house. If it's known that at least 3 of the drawn cards are aces, what's the probability of getting a full house? So this problem looks like a conditional probability. You see a keyword here. It looks like conditional probability. Let's translate the problem first. Let A be the event that at least at least 3 of the drawn cards are aces. Let B be the event that getting a full house. Let B be the event of getting a full house. So what we are looking for in this problem, A is given as a condition. At least 3 of the drawn cards are aces. A is given as a condition. So what's given as a condition, go to the back. What we are looking for is getting a full house. What we are looking for, go to the front. What's given as a condition, go to the back. What we are looking for, go to the front. Then use the formula. Probability of A intersection B over the condition, over probability of the condition. Then we find each one individually and then divide. Let's find probability of A first. Remember, probability is always number of feasible outcome divided by the number of all possible outcome. So for the denominator, the number of all possible outcomes, we are drawing 5 cards out of a standard deck of 52 cards. When we draw 5 cards, we don't care which card we get first. We care what card we get. So the order doesn't matter. The number of way of getting 5 cards out of 52 is 52 choose 5. Since the order doesn't matter. That's the denominator. Number of all possible outcome. Now numerator. Number of feasible outcome. At least 3 of the drawn cards are aces. If at least 3 of the drawn cards are aces, we may have 3 aces or 4 aces. If 3 of the drawn cards are aces, we may have 3 aces or 4 aces. If we get 3 aces, the other 2 cards cannot be aces. They are non-aces. We know that there are totally 4 aces and 48 other cards. In general, there are 4 aces and 48 other cards. The other 2 cards cannot be aces. We must choose the other 2 cards from 48 other cards. So if there are 3 aces, we choose 3 aces out of 4. We first of all choose 3 aces out of these 4 aces here. Then for the other 2 cards, we choose 2 cards out of these 48 other cards. At least 3 aces means it could be either 3 aces or 4 aces. If we choose all 4 aces, the last card cannot be an aces. So we choose 4 aces out of 4. For the last card, I choose it out of these 48 cards. That's 48, choose 1. This is probability of A. Number of variable outcome divided by the number of all possible outcome. That's probability of A. Next, let's try to find probability of A intersection B. Let's try to find probability of A intersection B. For probability, the rule is always number of variable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. We are choosing 5 cards out of 52, and order doesn't matter. It's 52, choose 5. That's the number of all possible outcome. Then for the number of variable outcome, we must consider both event A and B. At least 3 of the drawing cards are aces, and getting a full house. If we get a full house, and at least 3 of the drawing cards are aces, that means the triple here must be aces. The triple of cards must be 3 aces. And the rest must be a pair. The rest must be a pair. These 2 cards must be a pair. We must have 3 aces and a pair. So for 3 aces, we choose 3 aces out of 4. We first of all choose 3 aces out of 4. There are totally 4 aces. First of all, choose 3 aces out of 4. Now for the pair, we know there are totally 13 different ranks. There are totally 13 different ranks, from ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, and King. There are 13 different ranks. Since we use ace as a triple, for this pair here, it cannot be the same rank. So we choose 1 rank out of 12. We choose 1 rank out of 12. We can pick aces, but we can pick any other rank here. So there are 12 rank here. We choose 1 rank out of 12. So for the pair, I first of all choose 1 rank out of 12. Then once I pick a ring, for example, if I pick 4, there are 4 different 4s. It could be number 4 of club, number 4 of spade, number 4 of heart, and number 4 of diamond. There are 4 different 4s. I choose 2 of them to form a pair. Choose 2 of them to form a pair. That's 4, choose 2. We are choosing 2 cards out of 4. That's 4, choose 2. That's the numerator, probability of A intersection B. Then, together, probability of B given A is probability of A intersection B over probability of A, which is the numerator 4 choose 3, 12 choose 1 times 4 choose 2 over 52 choose 5. That's the numerator. Denominator is probability of A. Put this here. 4 choose 3, 48 choose 2, plus 4 choose 4, 48 choose 1, over 52 choose 5. Then use calculator, get an answer. Part B. If it's known that at least one of the selected cards are aces, what's the probability of getting 4 of a kind? Part B. If it's known that at least one of the selected cards are aces, what's the probability of getting 4 of a kind? 4 of a kind looks like this. For example, 4 cards of the same kind. The other card is different. Let's call 4 of a kind. Or could be Jack, 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 King. 4 cards of a kind. The other card is different. Let's call 4 of a kind. Let's call 4 of a kind. And this problem, it looks like conditional probability. We have a keyword here. It looks like conditional probability. So let's translate the problem and set it up first. Let event A. Let A be the event that at least one of the selected cards are aces. At least one of the selected cards are aces. Let B be the event of getting 4 of a kind. That's all we are looking for, getting 4 of a kind. So this problem can be written as probability of A as given A is the given condition. At least one of the selected cards are aces. So event A is a given condition. What we are looking for is B, getting 4 of a kind. So put a condition on the back. Always put a given condition on the back. What we are looking for, go to the front. What we are looking for, go to the front. What we are looking for here is getting 4 of a kind. What we are looking for, always go to the front. And what's given as a condition, go to the back. Then use the formula. That's the probability of A intersection B over probability of A. That's probability of A intersection B over probability of A. Then we find each one individually and then divide. Let's find denominator first. Probability of A. Probability of A, it says at least one of the selected cards are aces. At least one, maybe it means it could be 1 aces, 2 aces, 3 aces, or 4 aces. There may be too many cases. So to make it a little easier, let's think of the complement. To make it a little easier, let's think of the complement. What's the complement? What's A complement? A says at least one of the selected cards are aces. The complement means none of the selected cards are aces. None of the selected cards are aces. Probability is always number of viewable outcome divided by number of all possible outcome. Let's find the number of all possible outcome first. We are choosing 5 cards out of 52, and order of the cards doesn't matter. That's combination. 52, choose 5. For the numerator, what we are looking for is none of the selected cards are aces. If we don't choose aces, there are 48 other cards. We must choose 5 cards from here, from the 48 other cards. So the number of ways of getting 5 non-aces cards is 48, choose 5. That's probability of A complement. Then for probability of A, we use 1 minus probability of A complement, which is 1 minus probability of 1 minus 48, choose 5, over 52, choose 5. That's probability of A. Then let's find the numerator. Probability of A intersection B. Probability is always number of viewable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. We are choosing 5 cards out of 52, and order doesn't matter. That's 52, choose 5. That's the number of all possible outcome. For the numerator, number of viewable outcome, we must consider both event A and B. At least one of the selected cards are aces, and getting 4 of a kind. At least one of the selected cards are aces, and getting 4 of a kind. So there are 2 cases. Either we have 4 aces followed by a single card, or we have 4 of a kind and a single card is aces. There are 2 cases. Since we're getting 4 of a kind and at least one of the cards is aces, we are either getting 4 aces followed by a single card, or an aces is a single card. We have four of a kind. We have 4 of another kinds. We have a 4 of a kind with another ring. So there are 2 cases. Let's consider the first case. 4 aces followed by a single card. Let's 4, choose 4. We first of all choose 4 aces out of 4. Then for the single card here, we choose 1 ring out of 12. For this single card, it cannot be aces. For this single card here, it cannot be aces anymore. So choose 1 ring out of 12. After I pick a ring, say I pick 4. There are 4 different suits. It could be 4 of club, 4 of spade, 4 of heart, or 4 of diamond. We're choosing 1 card out of 4. There are 4 different kinds here. There are 4 different suits here. We choose 1 out of 4. It's 4, choose 1. That's a choice for the first case. That's a number of ways of getting 4 aces followed by a single card. Case 2. 4 of a kind other than aces followed by a single aces. 4 of a kind other than aces followed by aces. So let's make choice here first. We first of all choose a ring out of 12. We cannot choose ace, so we choose 1 ring out of 12. Let's 12, choose 1. After I make choice from the ring, say I pick 4, for example, I pick 4. There are 4 cards. There are 4 different suits. Then in order to have 4 of a kind, I must pick all this number 4 here. I must pick all these 4 numbers. Let's 4, choose 4. Then for the single aces here, there are totally 4 aces. We choose 1 aces out of 4. There are totally 4 aces. We choose 1 out of 4. That's the numerator, number of favorable outcome. So that's probability of A intersection B. Then for the conditional probability of B given A, we plug in probability of A intersection B and probability of A, which is 4 choose 4 times 12 choose 1 times 4 choose 1 plus 12 choose 1 times 4 choose 4 times 4 choose 1 over 52 choose 5. That's the numerator. Denominator is probability of A, which is this number. 1 minus probability of 48 choose 5 over 52 choose 5. 1 minus 48 choose 5 over 52 choose 5. Then use calculator for the answer. We can get an answer. That's probability of B given A.